I want to thank everybody for coming tonight for Mars 2020, Astrobiology and the History of the Red Planet. Tonight we have Dr. Aaron Coyner, who is a solar physicist by trade and the physics faculty part of the physics faculty at Southwestern Oregon Community College. He is also an avid amateur astronomer and a proponent for lifelong science exploration. Dr. Coyner has research experience, having spent graduate school at Rice University and a 3-year postdoctoral research term at NASA/Goddard Space Flight Center. He has 6 years of teaching experience at the community college and university level. Dr. Coyner also has lifelong experience with amateur astronomy and many years experience with astronomy clubs. This is my favorite line though. His overall goal as solar system ambassador is to make space accessible to everyone. He hopes to instill a sense of wonder and an increased desire for exploration among audience members of all ages and backgrounds. As a professor, Dr. Coyner relies on making tangible connections with audiences through comparisons to everyday life or familiar references. Thank you, Dr. Coyner, and it's all yours.
All right, thank you very much for that introduction, Paul. And we'll be as honest as we can with this. When I say that, where I
oh sorry, Dr. Coyner, unmute yourself.
That should work. All right.
Apologies, I thought it wouldn't mute the co-host.
That's okay. It's always a good idea to at least mute and recharge everything every once in a while. Anyway, what I was saying is thank you very much for that introduction, and I will do my best to make this as tangible and attempt to make this as entertaining as possible. Be aware there will be sarcasm, there will be interesting things, and there will be comic and cartoon references because I can't do a talk without them. Just be aware. This talk is on astrobiology and the red planet, looking at Mars 2020 and beyond. I'm mostly going to focus on the Mars 2020 mission, but we're also going to talk a little bit about the history of Mars as a topic and a hotbed for what happens if we find alien life in other places. This is part 1 of a 3-part series on astrobiology. 2 of these talks are done by me. One of the talk that you're in right now. Next month, we will have a talk hosted by North Bend Public Library on astrobiology of exoplanets. And in November, we're actually hosting a speaker at SWAC as part of our Physics and Astronomy lecture series. Dr. Tracy Becker from Southwest Research Institute in San Antonio, Texas, will actually be joining us for a discussion of NASA's Europa Clipper mission. She's actually one of the project scientists that works on the Europa Clipper mission. So rather than have me talk about Europa Clipper, I figure I might as well bring in an expert. So that's the 3rd one of our series. We hope you can enjoy all of them. So we talk about astrobiology, and it's a nice long word. Astro meaning star, biology meaning the study of life. So I guess we should probably focus on what exactly we mean by astrobiology. Well, when first trying to decide what astrobiology means, it's always good to consult the dictionary. So Webster's dictionary defines it as a branch of biology concerned with the search for life outside of Earth and with the effects of extraterrestrial environments on living organisms. Nowadays, that has sort of two different aspects of meanings, because we're looking at astrobiology in terms of what signatures of life can we find in terms of life that may be out there. And also we start to focus a little bit more on the what effects can extraterrestrial environments have on living organisms when we start talking about life at the space station for extended periods, prolonged human missions to Mars, which takes 7 months to get there on a good flight plan. While manned missions to Mars are still several years out, and probably a couple of decades actually, these are things that are currently being worked toward in terms of missions to Mars that are unmanned right now, trying to find ways to make the manned missions more possible. And we'll get into more of that in detail. Nowadays, we look at astrobiology, it's not only a field of biology, but it's become a very interdisciplinary field. You have physicists, you have astronomers, you have biologists, chemists, and other scientists, particularly situations like computer scientists and computer programmers, engineers, any number of different professional facets that team together to address what life beyond Earth looks like from a human perspective, and from a will we find anything in terms of different types of life and living organisms that we, and even biotracers of potential life that had existed long ago. So why are we interested in Mars? Well, in terms of planets in our solar system, I like to think of Mars as Earth's little stepbrother. And it's kind of Earth's stepbrother in the sense that it's in the edges of the habitable zone, in theory, of the habitable zone that would be created by our typical G2 main sequence star that is the sun. It's smaller than the Earth, and part of that actually likely has to do with just the overwhelming size of Jupiter. But it's much smaller in that it didn't have as much material left to collect to become a much larger planet. But because of where it is in the orbit, and because of the duration of the orbit, it actually has a climate similar to that of Earth, only slightly colder. It is colder. I didn't check the temperature today, but my guess is it was probably somewhere in the vicinity of 10 to 20 degrees, which is not pleasant, but not as completely harsh as some other places in the solar system. It also has a similar rotation period to the Earth, so that it has a rotation period of about 24.5 hours. So its day is slightly longer than ours, but it's not a drastic shift like Venus, that has such a small rotation period around its own axis that its day actually lasts longer than it takes to go around the sun. So Venus only has like one day all year, whereas Mars, its orbital period is about 1.8 or 1.88 or 1.9 years, and it orbits, and you get roughly the same amount of days as you would on Earth. So for us, that would be about a 700 day orbit. For Mars, it would be about 650 because of the extra half an hour here or there. But Mars has aspects. We know it has polar ice caps that are mainly made of dry ice, frozen carbon dioxide. There is some liquid water in various aspects of the polar region, and there have been signs from orbiter missions that we've seen since 2005. We actually see some evidence that there are craters on Mars that have noticeable surface, a few droplets here or there of potential surface liquid water. And we'll talk a little bit more about that as we go forward. I always thank the audience for checking. I guess today the high temperature was a balmy -14 today, so I was a little bit, I was hoping for a heat wave that wasn't exactly there, but most of the slides, in fact, probably half the slides that you'll see today actually come from a presentation that was given to us as Solar System ambassadors by Kenneth Williford, who is a deputy project scientist for the Mars 2020 mission at JPL. He actually included a lot of interesting information that rather than try to paraphrase, it was easier just to give him credit and give him the and use the slides as they were, because some of the information is really hard to paraphrase. So the reason Mars is really popular in terms of potential sources of life dates all the way back to the late 1800s. Giovanni Schiaparelli. Rather than true channels in familiar form to us, we must imagine depressions in the soil that are not very deep, extended in a straight direction for thousands of miles, and over the width of 100 to 200 kilometers, maybe more. I've already pointed out in the absence of rain on Mars, these channels would probably, channels are probably the main mechanism by which the water and with an organic life can spread on the dry surface of the planet. So you see this quote, and unless you see the actual map, and this is Schiaparelli's map from 1886, where he starts to document where these channels, or as Percival Lowell would call them later, the canals or canali on Mars, you start to see these little channels that develop that are hundreds of kilometers long, and they're visible through some mapping techniques through telescopes, although the original canals, as seen by Schiaparelli and seen by Percival Lowell, were actually due to an observational error with the lenses of the telescope, in the sense that they were actually starting, because of the magnification issues, they were actually seeing the blood vessels in their own eyeball that were actually creating sort of the canal patterns. Now we have seen in later images, and we'll talk about that in a minute. But yes, the reason that they were interested in these canals is they're thinking canals would be synonymous with water. If we had water, then there would be a likelihood that we'd have life. And this is almost a History Channel a History Channel show, but if you have life of some form and it's from Mars, it almost has to be aliens, right? Well, pop culture has run with that. So aliens on Mars, you get everything from the greatest of the Looney Tunes characters, and I'm willing to fight anyone on this call for that chooses to dispute that, but Marvin the Martian, the greatest Looney Tunes character ever. Or you have the 1996 movie that everyone would rather forget, known as Mars Attacks. You have any number of other Martian movies with appropriate Martian aliens. This is not necessarily the astrobiology we're talking about today, but this was kind of the direction that pop culture took it when it became possible that was there a potential of having life on another planet. So this is Percival Lowell, and you can see sort of the same type of globe, the same type of globe situation that you had before, as with Schiaparelli, except this is actually in globe form and you start to see where Lowell has actually created a map of the canals that he was seeing as well. Again, same problem with actually the multiplications of the amplification of basically looking at the blood vessels on his eyeball from being essentially too magnified at any given point. I'll stop and take a breath for a minute because I think we have a couple of questions in the chat. Paul, if you want to.
Well, I thought I saw Troy raise his hand. Did you have a question, Troy? You can go ahead and unmute and ask it if you like.
Never mind that. That was a error.
Oh, okay.
All right.
I think so far we just have a smiley face about the aliens, Andrea's stats on the temperature on Mars.
All right. So I'm just keeping track of things, but
Appreciate that.
all right. So one of the things that this led us to do when we got to the capability of actually getting to land things on Mars. We have various landers. We have the Viking 1 lander, we have the Viking 2 lander, we have Pathfinder, and if you look at the globe, you can see where the spots are. Viking 2 landed much closer to the polar region. Viking 1 and Pathfinder landed more equatorially. And pretty much regardless of where we landed, whether we're looking at the Viking 2 image, or we're looking at the Pathfinder image, or we're looking at the Viking 1 image, it's basically rust-colored rock. It's dry. There's not any appreciable water there. There's not a whole lot of difference really from one geological site to the other. We're basically seeing the same kind of structure, the same basically barren wasteland with rocks. And these are all landing sites for those 3 rovers. Subsequent rovers, you see very similar things. You see some variations because you have cliffs and you actually have basins and canyons and things, and you also have one of the largest volcanoes in the known solar system, Olympus Mons, which as a volcano, the base of the volcano is roughly the size of the state of Missouri. Was not particularly pertinent to this talk, so I left that slide out, but I will let you guys envision a giant volcano the size of, say, Mount St. Helens, except blow it up to the size of the state of Missouri, and you've got an idea of how big this volcano is. Well, if you look at some of the data, and these are images that have been worked with from NASA from some of the images in the last 10 years or so, you actually do see, from the satellite data, you do see these runoff channels. And in this case, these are not from astronomers staring at too high of a magnification for too long. These are actually visible runoff channels from high-def satellite images. So we know we see runoff channels, but we don't currently see large quantities of water. Although that has asked the question and has set up the question for many things about whether or not there was water on Mars at one point that would have eventually been vaporized away because of the relative lack of a protective atmosphere on Mars. Mars has an atmosphere, but it's not nearly as thick as ours, and it's about 96% carbon dioxide, so it doesn't really, what little atmosphere it has is not generally strong enough to hold water and volatiles and other things that would evaporate away if exposed to cosmic rays or other such solar particles from solar flares or other things. But we do see, if we look at, and this is an image from the Mars Reconnaissance Rover looking at the walls of a crater, and this is Garni Crater on the surface of Mars, and you can actually see the dark streaks. Those actually, whoops, go back because it's trying to run off on me again. These are actually high-resolution images from Mars Reconnaissance Rover, and the dark streaks are actually several hundred meters in length. And we can actually see kind of a seasonal pattern that indicates that there was at some point a temporary flow of some liquid, whether it's water, whether it's some other liquid that was propagating through. We actually do see evidence that there was water at one time. And more evidence, we're looking here at the Horowitz crater, and on the downslope, you actually do see the dark streaks that indicate that that there was some water and some water erosion. This thing is blown up a little bit so that you can actually see it in more detail, but you can start to see where there was some liquefied, some liquid flowing through it. And we suspect from the planetary geologist at the University of Arizona that that was actually at some point a liquid water stream that was flowing in and essentially eroding out part of that canyon, part of that crater, which makes sense given what we know about the topology of, or the topography of Mars. We have a lot of really deep canyons. We have Valles Marineris that's literally the Grand Canyon, except it would stretch all the way across the United States. So it's like if we took the Grand Canyon and put one rim at like San Francisco and stretch the other rim to Washington, D.C. It's one giant Grand Canyon that's that size. So at some point there had to be some degree of an erosion mechanism. We know there are winds on Mars, so there is wind erosion, but we would also suspect that at some point there was liquid erosion in the form of, say, water erosion or something else that was helping with that shaping of the terrain. So we go into this graph, and this is again from that training presentation that I had, and we talk about all of the different Mars missions from 2001 outward. We didn't go all the way back to the Viking landers because those are back in the 1970s and 1980s, and they can't necessarily fit on this particular slide. But since 2001, we have Mars Odyssey, which gave a significant amount of data. Mars Express from the ESA also has been orbiting and giving us significant data. We have Mars Reconnaissance Orbiter, which took some of the pictures that you saw previously. We have our MAVEN satellite, which is still taking data and providing information on Martian weather. We have the Trace Gas Orbiter, the Mars Orbiter mission, which all of those are currently in operation. Of course, we had Spirit and Opportunity, and we had the Curiosity rovers. The Curiosity rover and the Spirit and Opportunity, they had all orbited. They turned off Opportunity last year after it had been successfully giving data for roughly 15 and a half years. Its batteries finally wore out because, well, there was a dust storm that covered up the solar panels. And the dust blanket on the solar panels became too dark to actually still get solar power. And so it had a quiet demise. Last year, long about Thanksgiving, I think, we landed the InSight lander, which is specifically designed to look at the geology of Mars and look for Marsquakes. Earth has earthquakes, Mars has Marsquakes. We look for signs of geologic activity that might be essentially a sign of basically the more of a vibrant core of the planet and how much geologic activity and geologic turnover there may be. Recently, we launched in February. In July, we launched the Mars 2020 mission, which is expected to land on Mars. Here it's listed as the M2020 rover. It has since been named the Perseverance rover, and it was a 7th grader in Pennsylvania that actually named it. And we'll talk more about Perseverance later on in this talk, but it is designed specifically to look for signs of early biosignatures and also look for signs of more prevalent sources of water. And there's also instrumentation on it to attempt to take the carbon dioxide atmosphere that Mars has and attempt to make breathable oxygen out of it. And there are ways to do that. There are ways to do that chemically, and we're testing it essentially within the MOXIE instrument to see if it is something that we can make readily available for when we actually have humans that visit Mars. We would like to be able to actually have them breathe. Might not be one of those things that is particularly beneficial to the science of a manned mission if the entire crew has to hold their breath for the entire time, because that would be a very short-lived mission. And as you can see from the sort of from the bottom of this, there are various goals of what are we looking at in terms of Mars. We're looking for, we found evidence from Mars Reconnaissance Orbiter and others that there were traces of water, and now our goal is to basically follow the water and find, okay, where is it? Is it still there? Is it still usable? Can we find any of it? And then sort of as a second piece to that, we want to explore, okay, can Mars be habitable? We know the temperatures will vary enough that, but it's still on the edge of what we would consider the habitable zone. But could we actually make it a habitable destination for astronauts for an extended base? Or is it habitable for any other type of life that we may not have thought of yet? And then once we get past that exploring the habitability part, now we're kind of in the timeline where we're starting to look for signs of life or life that may have existed beforehand. And the whole time, of course, all of these are tying into prepare for future human explorers. Because if we know anything about humans, we always like to, when we find out that there's a new cool place that might be open for humans, everybody will flood to it for a while until the novelty wears off, and then they will. I'm basically expecting Elon Musk and whoever's in charge of the Walt Disney Corporation at that particular time to not only have space tourists going to Mars at some point in the very distant future, but at some point also there will be a Disneyland Mars. It may not be till sometime in like 2150 or something, but leave it to somebody at the Disney Corporation after they finish taking over all of media. They will find a way to build it. They will find a way to build a theme park on the Martian surface. But that may be 100 years from now. It may be 200 years from now. But that's kind of my long-term pipe dream of, at some point there will be capitalists on this rock we call Earth that decide to make tourist destinations out of Mars. Right now we can't do it because the amount of radiation that astronauts would have to go through in order to get to Mars for the 7-month minimum journey would basically irradiate everybody. So we don't have enough shielding or the proper amount of shielding to withstand that level of radiation for that length of time. But these are all things that are currently being worked on at various labs across the country and across the world. So this is a artist representation, but this is the InSight rover, or this is not the InSight rover, but this is the Perseverance rover. It is basically that same size. It has different instruments on it. We'll talk about those different instruments. It will land on Mars. I believe it's scheduled. The entire Mars 2020 lander is designed to land, I believe, on February 21st of 2021. So about mid-February, we'll go through about a 7-minute panic where they lose contact with the rover, only to hope that after 7 minutes it actually landed right and can talk back. But that's always a fun thing to watch. And I know when we do have the Mars rover lander, I'll probably have a Facebook stream going where people can chime in and watch along with us while we're waiting for the actual signal that it landed correctly. So mission overview, and this was a talk from October of 2019. It was launched on an Atlas V 541 launch vehicle. It was actually launched at the end of July. It was July 30th at 4:50 in the morning. It's currently in cruise control. It's got a 7-month cruise where it's been woken up a couple times just to make sure that it can still talk, but we're trying to save battery power as much as we can. And then in February, we'll have the entry, descent, and landing. And then when we get to Jezero Crater, which is the chosen site of landing, we have the rover capable of traversing about 20 kilometers of the surface. And we actually have about 1.5 Mars years worth of lifetime, which is about a 3-year lifetime of the actual mission, looking for signs of past life and collecting returnable samples that will eventually come back to Earth labs sometime around 2031 is what we are hoping. When we say that there's a 3-year mission on this thing, oftentimes the primary mission is about 3 years, and then they will often get extended because they last longer than they had intended to. Like I said earlier with Opportunity, it was supposed to last for 2 years. It lasted for 15. So they kept giving it more things to do because it was still actively wanting to send information. So we figured we might as well use it while it was there. And this is a little bit on the Jezero landing site. This is actually from JPL. Talks a little bit about this is a flyover of what the landing site should look like. They do fancy things.
This flyover was produced from NASA images taken from orbit. The blue circle indicates the area the rover will likely land. The arcing hills in the center, about 1,600 feet high and are the rim of Jezero Crater. The central goal of Mars 2020 is to learn whether life ever existed on Mars. It's too cold and dry for life to exist on the Martian surface today. But after Jezero Crater formed billions of years ago, water filled it to form a deep lake, about the same size as Lake Tahoe. Eventually, as Mars climate changed, Lake Jezero dried up and surface water disappeared from the planet. An ancient lake is a fantastic place to pursue our goal of looking for possible Martian life. On Earth, lakes are filled with living creatures. Evidence of that life is often preserved in the mud and sand deposited on the bottom of the lake. So, we use the rover's instruments to explore the rocks of the ancient lake bed. Here we can see evidence of the former lake. The canyon cutting through the crater rim was carved by a river. As the water entered the lake, it slowed and dropped the sand and mud it was carrying to form the fan-shaped delta. The white line is a path the rover might follow in its first 2 years, called the prime mission.
You need to do that.
As Mars climate changed, of looking for possible Martian life. In mud it was carrying to form the fan-shaped delta. The white line is a path the rover might follow in its first 2 years, called the prime mission. During this period, we use the rover science instruments to analyze the lake sediments. After we explore the delta, we hope to investigate the shoreline of the former lake. To get there, we have to traverse around a sea of modern sand dunes. From this perspective, you can see former shorelines curving around a headland. We can picture waves in Lake Jezero beating on a sandy beach. And finally, we will press on to the crater rim. Jezero Crater formed when a large object collided with Mars, excavating rocks from deep in the Martian crust, exposing them in the rim for us to study. These rocks would have been hot shortly after the impact and may have hosted hot springs. Deposits from these springs would be another target in our search for possible ancient life on Mars.
So that's a little bit on why exactly they want to go look at the Jezero Crater. The mission objectives, in short, we want to look at the Martian geology. We want to explore the ancient environment. We want to understand the processes of formation and alteration that changed the surface of Mars the way it did. We're looking at astrobiology, so we're looking at assessing habitability of the ancient environments. And we're seeking evidence of past life. And doing so, we're actually taking samples of the Martian surface of regions that we find that have high biosignature preservation. So it's when we're starting to see things that have biosignatures in them, we have a way of actually collecting the samples. And the hope is that between this mission and a mission that comes in 2026, and also one that comes in 2030, that we'll be able to have a full sample return to Earth from Mars by 2031, I believe is when they said they were aiming for. And a lot of that timeline has to do with collecting the samples to begin with, and then has to do with the orbital mechanics of trying to make the shortest trip to Mars and then back from Mars in order to make the sample return mission. And of course, the last part is to prepare for human exploration. So we measure the temperature, humidity, wind, the dust environment, and we want to demonstrate the ability to convert the atmospheric CO2 into oxygen so that humans could actually breathe. In a little more detail, the mission overview looks at basically looking at if the past environment was capable of supporting microbial life. We look for those past signs of microbial life in terms of chemical composition, in terms of is there evidence of water or evidence that there was water at one point? Are there evidence of organic compounds that would have been either necessary for or a byproduct of having microbial life there? We are collecting samples by essentially taking cores similar to what we would do at the Antarctic ice shelf, where we basically would dig down and remove a core of the ice and then look at what the composition was of that particular ice. In this case, we're looking at the composition of the soils from the surface level to the subsurface. And again, preparing for humans, so we're testing to see if we can make oxygen. Okay, so this is the Jezero Crater, this is the Perseverance rover, which will be exploring Jezero Crater. We have any number of instruments. We have the main rover itself. We have the RIMFAX instrument, which is at the back of the rover, which is actually a subsurface radar. It allows us to get an idea of what the structure of Mars looks like below its surface by basically using ground penetrating radar. We have the MOXIE instrument, which is basically the middle part of the rover itself, which is the oxygen production method. We have MASTCAM, which is a zoomable panoramic camera, so we can actually see all the cool pictures of what the rover is running over or running into. META is the weather station. It analyzes temperature, humidity, wind, dust particulates, and various other aspects. And then we have sort of my favorite part is the Sherlock, Watson, and Pixel. Sherlock is an ultraviolet spectrometer. Pixel actually is an X-ray spectrometer, and Watson is the super camera that ties all of that together. But what that actually allows us to do is it allows us to look at the images that we're taking in X-rays and in ultraviolet to look for signature emissions from organic compounds. Certain things, my background is in solar physics, so we talk a lot about ultraviolet lines because we start looking at ultraviolet lines of iron because it gives us an idea of how hot the solar flares are. So in this case, we'd be looking for ultraviolet lines, but we would be looking for ultraviolet lines that specifically correspond to the spectrum of organic compounds, hydrocarbons, water, more carbon dioxide, more additional essentially organic compounds that would be essentially created by the existence of microbial life at one point. And signatures of this could be trapped in the rock formations because they would have trapped within the rocks before they hardened, and they may not have been able to outgas completely. So there may still be signature traces of these elements and these compounds within the rock structures. And the easiest way to determine that is to do spectroscopy on the images and also to do sample returns. But the spectroscopy on the images will be much quicker because the sample return mission will take 10 years. There's just a better image of or a better or artistic representation of the actual images and everything else involved. Okay, so this is the fun part. This is a rover that has a companion to it. And I told you the rover is called Ingenuity, or the rover is called Perseverance. The helicopter that goes with it is called Ingenuity. And the helicopter, and I got to show the video because that's just fun. Open on my other screen, but it'll work. Can you guys still see that? Because it opened to a different thing, so I don't know if it popped open to where.
We can only see the presentation.
Okay, well, I can fix that. Let's do.
I thought you could.
But that's why I asked the question, is because then I can.
Now we can see it.
NASA's got all their fancy stuff that they do. The rover in specific, we'll go back to the PowerPoint. The rover in specific is doing all of its missions with all of the different instruments that we talked about. The helicopter is designed with a camera to be able to take essentially surveillance and drone photos, just to fly over certain regions that the rover can't get to and take high-res pictures. But a lot of the reason for the helicopter is to show whether or not it is actually possible to do technology like that with a drone helicopter in the Martian environment. As I said, the atmosphere is much thinner, so a lot of the forces in terms of lift and drag and other atmospheric forces that are necessary on Earth to keep helicopters stable and help keep them flying are not as prevalent, or they do exist, but they're not as strong in the Martian environment. So getting a helicopter to remain stable in the Martian environment is still a question that we have an entire science team that has put together how this should work, but this is in some extent a proof of concept as to whether we can do drone reconnaissance and things on Mars if we're looking to do future missions and for manned missions as well. Because if there is something out there worth looking at, and we have a manned mission, we would like to be able to send something out to take pictures of it before we send the astronauts into harm's way. That's just me, but I'm sure the astronauts would be perfectly fine. If you want to look more into the Ingenuity helicopter thing, there is a link to it, and I will share these slides with you, Paul, and then you can, and then if somebody calls, or Andrea, I can send them to you too. But if anybody calls either one of the libraries and they want the links or they want to see the slides again, you guys are welcome to share them.
Sounds good. I'll throw my email in the chat box.
And so here's kind of the idea of how, say, a sample return mission would go. So you would essentially send a mission in from the Earth. It would cruise, it would land. While it's on Mars, it would collect samples. And then from Mars, you would essentially launch it up to a launch it up from Mars to a sample, or to a satellite that we actually had in orbit that would then return back to the Earth. And that's one of the reasons why this takes 10 years to do. Because you not only have to get things to Mars, but you have to successfully collect stuff and then get it off of Mars and get it back. And at the easiest amount of time, we're dealing with the orbital transit period between getting off of Earth into Mars is at best 7 months. At worst, it can be almost 2 years. So it becomes a question of what is the time frame that we're looking at, and how many of these things can stay on the radar long enough to not become political football if we get delayed. Everything with NASA becomes a political process because we are a government agency. It is at this point in the talk, because I usually do this at the very beginning, I am a solar system ambassador through JPL, but as they would generally prefer me to mention, the opinions, rants, and otherwise diatribes of Dr. Aaron J. Coyner are his opinions and his opinions alone, and do not in any way, shape, or form represent any of the leadership at NASA, any of the many sane people that work there, and potentially the many insane people that work there. I say that because I used to work there, so I know there are insane people that work there. Because they used to hire me for crying out loud. And so what we're kind of looking at is we're looking at an exploration model where we're looking for geologic and astrobiological context. So what we'll look for is you'll look at SuperCam and you'll be able to see, okay, the structure from MastCam of what does everything look like. So we're looking for remote chemistry and mineralogy. Watson gives us sort of proximity images of what the pixel cam and everything else is looking at. Pixel and Sherlock will then analyze those Watson images in ultraviolet and in X-rays, looking for specific signatures at specific wavelengths to correspond to certain biosignatures. So we get a lot of chemistry in this, a lot of physics, a lot of engineering in terms of the different cameras, and this is of course partially into a biological exercise looking for biosignatures, and you've got the geology of looking essentially for stability within the subsurface, and you're also doing some geology and geosciences in terms of the coring of the samples and bringing the samples up from the subsurface. So it truly is an interdisciplinary project. So what can we actually look for? Well, we can look in the rocks and we can actually see potentially life-like patterns within the banding structures. If we find concentrations of biologically important elements or minerals, we can actually notice those in the ultraviolet and in the X-rays. And so this is like a, and this is actually a 3.4 billion year old fossil microbial mat that we have from Earth. But if we see something similar to this on Mars, we have the ability to detect. We have the ability to detect it with the various instruments that we have on the Mars 2020 rover. And so, if we look at something like our example microbial mat, and we look at it through pixel, you can look sort of in this box, and you start to see these regions of, again, interest, because of the green indicates potential, again, microbial signatures, and we can see them through this. And this is just that red square or red rectangle there that Pixel is looking at. And what Pixel would do is it would scan the entire rock and look for where are those signatures the strongest. And if there were enough signatures on it, then the other instruments that do the sample coring could actually then take a sample core of that area so that we have it to basically bring back and study when it comes back to Earth in 10 years. So Sherlock would look for the same thing. We're looking for, again, silicon, calcium, and iron in this case. And then we're looking, so the silicon is the green, the calcium is the blue, the iron is the red in the pixel. And then if we're looking at Sherlock, essentially the red is a quartz deposit. The dark blue ends up being a deposit of dolomite, and the green in the ultraviolet becomes basically a signature of organic carbon. And so we would have essentially the sample return part. We have the robotic arm with the turret that would actually dig down where the Sherlock and Watson and Pixel images are, and then we're able to gather up the essentially the sample core into one of 42 sample tubes, and then we would put that back into essentially the center of the rover for safe storage until time to send it back to Earth. This is just some of the coring images and the coring, the different methods for the coring. We've got the coring bits. We've got ability to dig into the Martian surface. I know InSight rover has a similar thing, and at times it got stuck because of the fact that various aspects of the Martian subsurface were much harder than we thought it was, but we did actually get it unstuck, which is always good. And that's kind of the end of the Mars 2020 thing. And I always close out an astrobiology talk because really for this one, we're talking more about astrobiology from a what could have been or what may have been a long time ago. But anytime I wrap around an astrobiology talk, I always bring us back to sort of the Drake equation, because this is the equation that has very much a lot of unknowns right now, but it's the equation of what is the potential number of technologically advanced enough civilizations that we could make contact with within the Milky Way galaxy. And there's a lot of different pieces to this. There's the rate of formation of stars. There's the formation of the fraction of stars that actually have planetary systems. I'm gonna sort of foreshadow part of next month's talk at North Bend, but that that fraction of stars that have planetary systems with current data and the current statistics of what we see from exoplanets, that fraction is probably very close to 1. It looks like most stars have planetary systems of some description. Whether that's anything that resembles our planetary systems, we're not entirely sure of. But these are things that are available and things that are here. In terms of once we get that number, you then have the number of planets in each solar system, with basically the possibility of being habitable for life. So what's the number per planetary system of planets that could be in the habitable zone? And then the number of habitable planets where we actually see life. At this point, that's essentially 0, because we know we have life here, but we haven't seen life in other places yet. And then we have the fraction, essentially, once we have life existing, the ones that we can start to get to evolve beyond like unicellular life and microbial life, can we start to evolve into more sentient life. And then there's the fraction of civilizations that develop technology able to communicate. And then of course the last one is, how long does it take them to do that, and how far away are they, so that we can figure out if they even had time to talk to us yet. So there's any number of these that, most of these are actually unknowns, but we're starting with research that's been done in the last 2 to 3 decades. We've got a fairly decent handle on the rate of star formation. And as I said, the more we do exoplanet research in the last 3 decades, we started to sort of isolate that fraction of stars that can form planets is almost entirely 1. It may be 0.99 something, but it's very, very close, very, very close to 1. Now, the rest of this right now is all speculation because, well, we have to actually get to where we can analyze more of the planets and then also start looking for for the life signatures that we'd be looking for. So are we going to find answers to the Drake equation anytime soon? No, but any work we do on astrobiology also increases our understanding of that, because it also makes the number of, say, locations where life could have been in our own solar system greater than it currently is, and that changes this equation slightly. So if we were to find something in the subsurface ocean of Europa, then that would give us another data point to work with. If we were to find that microbial life did exist on Mars for an extended period of time, and we could find the necessary and we could find the evidence for it, and we could find the conditions that were right for it, we could then figure out what more of a constraint on what is required to have life as we know it. And I will take a breath for now, and that's the end of the talk. I'm going to take a breath for a minute or two, and if we have any questions, then people can feel free to ask.
We do have one for you, so let us know when you're ready.
All right, go ahead.
So Susan was wondering how you feel about the recent findings in the Venusian atmosphere. Could it really be traces of life?
I am skeptical of that one. I did see that the other day. One of my former advisors sent it to me. I'm a little skeptical just because of the overwhelming disaster that is the Venusian atmosphere. 750 degrees and 90 times the normal atmospheric pressure, and oh, by the way, sulfuric acid rain. Not something I necessarily want to deal with, but if there is life that wants to survive there, it would be interesting. I have seen some of the data curves, and I know they're claiming that it's like a 15 sigma spike, and I think it's phosphine. But I think we'd need to do further study, because I think that their data was kind of jumpy in terms of the amount of scatter, and exactly how significant it would be, I'm not sure, but I won't put it past the fact that there could be something out there, because one of the things we find out as scientists all the time is there are things that we don't know. So there are always the possibility that we could be looking for life the way we expect it to be, but it could be completely different than what we anticipate it being.
Susan said thanks. Thank you. Dr. Coyner, are we done with your presentation? Can we stop the screen share?
Yeah, I can stop it.
Thanks. Thank you. Anybody else have any questions? You can go ahead and unmute if you like, or comments or anything.
Hi, can you hear me?
Yes, Carolyn, go ahead.
I was wondering if you think the recent phosphine discovery on Venus could affect the funding of the Mars missions in the future, because there will surely be a diversion of funding, certainly from the outer planets and their moons to Venus in a hurry globally. And I wonder what the effect might be on the Mars missions in the future.
I think from that perspective, you'll still see some you will see some increased attention paid to Venus, but Venus was never really a target for potential manned exploration because of the things I mentioned before, with the 90 times atmospheric pressure and the 750 degrees in the shade and everything else. So a lot of the missions to Venus might be more probe-based, looking at like smaller craft and nothing particularly human carrying. So there's a chunk of the Mars budget, because it's sort of been set out as a long-term goal that NASA wants to eventually have a human presence on Mars. And I think that's
I agree. I guess I was thinking a little more exotically. I've taught solar system astronomy decades ago, and though I'm more cosmology, they thought they'd play a joke, but I loved it. And so I was thinking of things, you know, a little more exotically in the more distant future, not habitation so much as, you know, I know Russia thinks it belongs to them, so terraforming, things like that, just the upper atmosphere.
Yeah.
Definitely things can be done on the more exotic side with balloons and all that.
I could see people definitely doing more missions like that. I don't know how many of them are in the pipeline, and I do know that those pipelines tend to be fairly long, so we'd probably be looking at 3 to 4 years to begin with before.
Right. Okay, thank you.
Before any of them would get off the ground, but it would be interesting to see more studies.
Susan added, we still have to explore our own black smokers on the ocean bottom.
Yeah, we do. We definitely have to do that. We definitely have to do that, and that's part of. We actually do a lot of research with that in order to kind of get an idea of what kinds of extremophiles we might actually find in the subsurface ocean of Europa, or at any of these places that are in the habitable zone around other stars that we can't actually go explore. We start to think, what kinds of extremophiles do we have on Earth, and can we simulate some of those environments?
Thank you.
I do want to take a little bit of time and not I didn't want to take away from the actual presentation itself, but I do want to keep the community in mind that we at SWOC, we are doing a lot of space-related activities, and we do have a lot of teams that are involved in various things, and I do want to talk about that a little bit. Right now, if you go to the Coos History Museum, we have an exhibit up at the History Museum talking about the 30th anniversary of the Hubble Space Telescope. And Crystal Hopper, who is my department coordinator and my best friend, and generally helps with all things space related in this town, among other things. she has curated the exhibit, and many of my students, I think Troy's still in here. I know he has a couple of pieces that are in the exhibit. We had 37 students at SWAC that contributed art of various types, discussing both the science and just the artistic sort of inspiration caused by Hubble images in general. And that art exhibit is currently at the Coos History Museum through, I believe, the end of September. We're going to try to keep some of it in the History Museum through October, although we're having to sort of relocate to a different space. So toward October, it'll shift a little bit, but I do encourage anybody interested in that sort of thing to go check out the students' work. I know Crystal did a great job of curating stuff, and the students did an amazing job of putting work together for it. Some of it was actually class assignments. Some of it was just extra credit that people wanted to do to help us out with celebrating that anniversary. Another thing we do have our Spear project, which is our balloon launch team. We're actually working now with our friends at Portland State that are getting ready to launch ORSAT, which is Oregon's first CubeSat. And we're working on test protocols for their ORSAT Live, which essentially means we're making small versions of ORSAT that go up in the high altitude balloons and then broadcast video down to ground stations. Because one of the ideas of ORSAT Live is they're going to have Wi-Fi cameras on the ORSAT itself that will essentially do a flyover of coordinates in Oregon if high school students or if libraries or if college students put in their coordinates and request a flyover. They will actually give you a time and a place for the flyover, and if you have a ground station, they will actually beam the video down from space of what the satellite is seeing as it's flying over your location.
Very cool.
And so we're working with them on some test stuff with regard to that. We have coming up in September, we'll have more what are called NASA SCORE projects, which are individual student research projects that are NASA funded through the Oregon Space Grant Consortium. And we'll have any number of space projects. And I'm going to encourage anyone that is interested, or if you have a SWAC student that may be interested, have them contact me. The easiest place to get a hold of me or get a hold of Crystal to set something up is to go through go through Facebook and go to Southwestern Oregon Physics and Engineering. All of our events are listed on there, and then we're usually fairly responsive to messages to try to get students involved or get out to the community to do more talks like this. So I would encourage anyone that's interested to feel free to reach out to us.
And if people contact us at the library about doing some of this stuff, is it okay if I share your email?
Yeah, that's fine.
Thanks, sir. Excellent.
I'm always open to this.
Drea, did you want to announce that next event for us?
I would love to. Our next talk is October. Oh, come up here. I just had it up, and so of course it's disappeared. It will be on exoplanets, and I believe that is October 8th. Yes, at 6:30. No,
I thought it was the 15th.
It is the 15th. You are right. I am wrong. The 8th is another project I do with Paul. So on the 15th.
That's the book club.
Yeah, the book club. It's totally very crossable, very crossable. People can do both easily.
Yes, definitely.
But yes, we'll be talking exoplanets. And I'm really looking forward to that, especially in the light of what you've been telling us here, Dr. Coyner. You know, and I like the idea of imagining what it's going to look like in Congress with people fighting for the Venusian project, and just you know, and you know, this all sounds so interesting, and I cannot wait to see what comes up with the October 15th program. It will be at 6:30. We have our own link for it, and I'm sending out the promotional material tomorrow. So it'll be on our website, it'll be on Facebook. Paul will probably cross-promote it as well. Dr. Coyner might, you never know. And
I shamelessly plug everything. You should know.
yeah,
this.
I know, yeah. Shameless promotion department, West Coast, we appreciate it.
Yes.
Yeah, we will hope to see you all then and invite your friends.
Yes.
Great, thanks, Drea. And if you guys want to find more Coos Bay Library virtual events, we're doing, of course, a lot more virtual events during COVID. You can go to coosbaylibrary.org and click on our events calendar. Anybody else have any questions for Dr. Coyner? Well, thank you so much, Dr. Coyner. I learned a lot, and looks
No
like
problem. I very much enjoyed it.
Likewise. Thank you, everybody, for coming.
Thank you. From Toronto.
Wow, awesome. Thanks for joining us, Carolyn.
Well, I just happened upon it. The joy of the internet.
Yes.